Now let's discuss recovery methods using substances not normally found in the reservoir. There are several. The first is thermal recovery. It is preferred for heavier oils, especially oil with about 20 degrees API gravity or less. These heavier oils also usually require a secondary recovery mechanism earlier in the production cycle than lighter oils. In thermal recovery, heat is injected into the formation, reducing the viscosity of the oil, allowing it to flow more readily into the producing well. As in water flooding, injector wells must be drilled, increasing costs. Instead of water, though, heat is injected into the well. In certain conditions, however, that heat can be created in the reservoir itself. There are three techniques used in thermal recovery. Some more successful than others, but each offers specific benefits. In the first technique, called fire flooding, a compressor at the surface injects air down into the injector well, providing oxygen to ignite the oil in the formation. The fire is controlled by how much oxygen is injected. The heavy crude oil is heated by the combustion of these hot gases, thus reducing its viscosity. This method is only partially successful because the colder, heavy oil located away from the burning heat source persistently resists flow and can even block the flow of the heated oil into the well. Additional injector wells can be drilled closer together to reach these cold spots, but this can prove to be a poor economic solution because this method consumes the oil itself and reduces it to useless char. Fire flooding is considered a final recovery method. A more efficient mechanism in thermal recovery is called steam flooding. In this technique, steam is generated at the surface and injected down into the formation. As the heavy oil is heated, the steam cools and condenses into hot water that is then allowed to soak into the oil near the injection well. This heat reduces the viscosity of the soaked oil, which can now be pushed toward the producing well. The cooler, heavy oil, away from the heat source, however, is not affected and may impede the flow of oil. Steam flooding can be very successful in shallow reservoirs where numerous injection wells can be drilled economically. The most efficient and therefore the most successful form of thermal recovery is called cyclic steam flooding, or huff and puff. Here, a well will operate as both an injector well and a producing well at different times in a cycle, thus the name. In an injector well, steam is injected into the formation over a period of 7 to 10 days. Steam injection is then stopped for a few days, allowing the steam to cool to hot water and soak the oil around the injection site. When deemed ready, the injector well now becomes a producing well for 7 to 14 days, pumping out the less viscous heated oil. After pumping out this heated oil, the producing well becomes an injector well and the cycle begins again. The advantages of using cyclic steam flooding are many. It is considered to be a relatively cheap technique because it does not require drilling a large number of tightly spaced wells, and it sharply stimulates production. Because cyclic steam flooding can be used to produce a well for years, it is an excellent secondary recovery mechanism for heavy oil. Miscible flooding is another secondary recovery mechanism. Usually applied after primary depletion and secondary water flooding have already been used, miscible flooding is more commonly used as a tertiary recovery mechanism. If you remember from your chemistry, a miscible fluid mixes with another liquid to form a single homogeneous substance, like water mixes with milk. This mixture does not change the molecular structure of milk. It just dilutes the milk or makes it watery. Miscible flooding depends on using a fluid that mixes with oil. This fluid does not change the hydrocarbon molecule structures. It just dilutes the oil making it less viscous. By the way, fluids that do not mix with oil, like water, are called immiscible fluids. Utilizing the miscible flooding mechanism, a reservoir is flooded with a fluid that is miscible. This fluid causes changes in the reservoir fluid characteristics. For example, it can lower the oil's viscosity. This, in turn, allows the miscible fluid to penetrate more deeply into remote recesses of the reservoir, lowering the trapped oil's viscosity and thereby allowing the oil to flow more easily. Carbon dioxide, CO2 gas, is an example of a miscible fluid with oil. It is used effectively in miscible carbon dioxide gas flooding. CO2 can occur naturally in the underground reservoir along with the hydrocarbon gases. When using CO2 in miscible flooding, it is either harvested at the well site or it is transported from another area by pipeline. The CO2 gas is then injected under pressure into the well. Once injected into the reservoir, the CO2 mixes with the oil, causing it to expand while lowering its viscosity in the reservoir. CO2 works best when it is used alternately with a slug of water because the water helps keep the CO2 moving evenly across the formation. This is referred to as a water and gas or WAG process. Using the WAG process improves the sweep efficiency because more of the reservoir rock is in actual contact with the advancing gas being pushed by the water. The major expense in CO2 gas flooding is the investment in the surface facilities needed to separate CO2 from the hydrocarbons. Fortunately, once the CO2 has been separated from the other gases, it can be compressed and re-injected back again into the well, allowing for a continual process. In addition to CO2 gas, there are other effective miscible fluids. Among these are liquefied petroleum gases, or LPGs. Although resulting in high recovery, using LPGs is usually too expensive, especially when the LPG market price is high. Flue gases can also be used. Flue gases are waste gases that are released in industrial processes using oil, gas, or coal. Being able to efficiently use flue gases in miscible flooding is limited because most of these flue gases are not readily available. Nitrogen extracted from air can also be used in miscible flooding. However, nitrogen is only miscible in deep reservoirs with very high pressures. Detergents are another miscible fluid. When used, detergents are injected into the formation followed by a water sweep. Again, although high recoveries are possible, the cost of detergents can be a deterrent. Alkaline or caustic substances can also be injected into the well for high recoveries, but they are usually unpleasant and unsafe to handle. Like detergents, these caustic substances are also very expensive. Mobility ratio is a fourth type of secondary recovery mechanism. Here, polymers, long-chain chemical substances, are injected into the well and help reduce the friction or surface tension between the water and oil molecules and the rock surface. Polymers have shown promise when coupled with water flooding. Water injections into the well are alternated with injections of water mixed with polymers. The high cost of polymers limits the economic feasibility of using this method. The fifth and last secondary recovery mechanism that will be mentioned here is the microbial flood. This process can be very useful under certain conditions. When using this mechanism, crude oil-eating bacteria are injected into the well. As these bacteria consume the oil, they produce a byproduct called methane gas, which is very miscible. As this methane gas is released from the bacteria, it creates pressure which pushes the less viscous oil out toward the producing wells. As you can see, using miscible and microbial flooding in a secondary or tertiary drilling plan can have high recoveries. Each has advantages and disadvantages. However, because of their cost and accessibility, their use is limited. Currently, a lot of research is focused on finding ways to improve these technologies. So let's review. We have many different drives or types of energy that are used to push hydrocarbons to the surface. These drives can be the Earth's natural sources of energy, like water, gas, gravity, or compaction. They can also be man-made or man-harnessed, like water flooding, thermal flooding, miscible flooding, mobility ratio polymer flooding, or microbial flooding. Whether used in primary, secondary, or tertiary recovery drilling plans, these drives allow us to get high volumes of hydrocarbons to the surface cheaply and efficiently. Now let's turn our attention to another important task for reservoir engineers. They must calculate as accurately as possible how much recoverable hydrocarbons are in the reservoir. These numbers are extremely important because they determine the future developments of the reservoir based on the value of its assets. But what are these assets or reserves? Defined by the Society of Petroleum Evaluation Engineers, SPEE, reserves are estimates of the volume of crude oil, condensate, natural gas liquids, and associated substances thought to be commercially recoverable in the known accumulations of oil in the reservoir from a given date forward. In other words, reservoirs are the current value of all the marketable substances in the reservoir that has not yet been produced. Oil companies want to be assured of how much production of the different petroleum products they can expect before they continue investing more money. In arriving at an amount accompanied by the value based in dollars, the current value of hydrocarbons is based on the price in the marketplace. In addition, they also calculate the costs of adhering to existing governing regulations and the cost of extraction based on current technology. These reserve estimates are used to determine the potential value or wealth of an oil company. Remember that since oil reserves are hydrocarbons still in the reservoir, their recovery rates can only be estimates. In ascertaining how much oil can be recovered, however, assumptions and estimates can be made with the full understanding that they are based on considerable uncertainty. The future market price and advancements in technology, for example, can impact these projections significantly.